Yeah, so guys, let's start. So this week we'll be completing some of the stuffs which were left in the last two workshops. So till now we have covered the text processing in bag of word model, n-grams and TF-IDF, and word embedding models. And last workshop, we went over RNN, LSTM, GRUs, and attention mechanism was left. So today we'll be covering cross attention mechanism and the coding part for RNN, LSTMs, and the word embedding models. And in the next workshop, we'll be starting with the transformers, and we'll be going over the architecture of GPT and BERT. So first, let's complete the coding part for word embedding models. So
Yeah. Am I audible? So in the previous workshops, we have gone through the word to vec and glow models. So basically, what it means is, so we'll with with a series of text. I mean, with the data set, we'll be predicting the word sequence. So basically, this is what's been going for the last two workshops. So the glow model, we we are using a library called GenSim. So and we are using a data set called glow.6p110. So this will be available. It is posted in the group Discord server. So in order to use the GenSim, we have I have converted it to word to vec format because the GenSim only processes the word to vec format. It doesn't exactly directly process the actual data. So with this function converts the glow data set into the word to vec model, and then this piece of code converts the loads the word embeddings into the model. Word embeddings is like just converting the words into the numerical dense format in order to for the computer to understand. So, okay. So this function, this gets the word vector. So we use this function to get the value if the word exists or not. It is, if it's related, how much relation, how similarity it has to the data sets. Imagine if it's the word is cat, it will determine whether how much similarity it has to the data set. So in the next steps, we'll be calculating the similarities. Here, if you can see, we got the similarity score with this function where get word vector. So these are the words we are putting it as input: cat, dog, house, and computer non-existent world. So we are just printing out the first 5 lines of the output which we fed here to this function. So the data set what we gave, the glow.6b, as like this much similarities. The sorry, yeah, here in this function we are giving the word cat as input, and the word cat as like the similarity score for the cat and the dog is 0.878, and the cat to trap it is 0.7424, and cat to cat is 73, and monkey is 72, and pet is 71. So these are the similarity scores we got. And here, so basically we are predicting the sequence, the relation between two words. So in the last step, we are giving the words woman and king, and the negative as word as man. So the most related word is queen. The king, man plus woman, which is similar to queen. The woman king will be called as queen. So this is that. And in order to show the limitations of data set, I mean, we used a pre-trained data, which is Glow 6B, and then we converted it to WordBack and we just used it. So we got the actual actual output. I mean, king, man, woman, it gives queen. So this is a good result. I just wrote another code in order to show if if we are lacking in the sense of data set, we have limited data. Of course, we will not get the actual output. So I just use this word to vec algorithm again. I use NLTK. This is the data set I gave. Just couple of sentences, which speaks about kings, queens, and other things. We are pre-processing the data here. We are just, if you would have attended the previous sessions, we are just pre-processing the text. We are just tokenizing the text. We are getting it to the lower text, lower case, and then tokenizing each tokens, which is the words. And then we are removing the stop words as well. And we are just returning the processed sentences. Here we are training it to the word-to-vec model. Now we are checking it if which socks are not king, man, woman, and queen. What we did with the same with the glove as well. So here, if we see, we are finding the similarities, but we are getting younger because we have a limited data sets here. We only have a couple of sentences to process the data, so we don't have enough input to get the output. If we give the inbuilt output, if you would have give the glove same again, you would have got the same. I mean, we would have got the queen as output here. And you can see the similarity scores here. The king to the younger quest writes and process. So it just gave us the most closest word that it can find in the data set.
Yeah. So guys, for those of you who are attending it for the first time, so word2vec and glove are like word embedding models. So embedding models are basically to convert word into vectors so that we can do computations on it. Because computers can't understand words, right? We can as humans, we can understand languages, but machines can't understand it. So to make the machines understand natural language, we first convert it into numbers. And in the previous workshops, we saw many different matrices like co-occurrence matrix, where we, based on the document, we just represent the number on its frequency, based on its frequency. But we showed that it's not very useful. It's not a very good representation of words because let's say we have some words which have different meanings based on the context. Let's say the word bank. So it can mean the river bank, or where we go to deposit, or the Constitution Bank. So based on the context, it can have different meanings. So if we take any model which just represents the word based on its frequency, it won't capture this relationship or the semantic meaning of the word. That's why we studied word2vec and glove, which actually capture the semantic meaning of the word. And so as you can see, and these are dense vectors. Dense as in there are very less number of zeros that you will find in the vector. And one more advantage of using word2vec and glove is that you can do interpolation between vectors. As you can see, like what I mean by interpolation is you can do logical computations. For example, king minus men plus women gives queen, which is a logical interpretation, right? If you subtract the vector of king, subtract the vector of men from king and add the vector of women, you'll get queen. So these kind of logical interpolations you can do. And the one thing which like Prabhakaran showed using this sentences example is you need to train these models word to vec and glove. These are neural networks, so you need a lot of tokens, a lot of data. That's why if you see the pre-trained model, it's glove 6b represent the 6 billion model, like, so it's trained on 6 billion tokens. That's why you are getting good representations, and that's why you are able to do the correct interpolations. But if you use, if you see this, uh, like these x like 10 or 12 sentences, it will, if you just train the model on these small number of data set, it will not produce good representation of words. So one like disadvantage is you need tons of data to train these models. So yeah, so you can go and play with this code and check and train your own word embedding model. uh, I'll quickly cover cross attention, which was left in the previous workshop. So in the previous workshop, we went over language models, and we studied different kinds of language models. Um, Excuse me. Yeah, so we studied what language models are, what are discriminative and generate, what do we mean by discriminative and generative models, and what autoregressive models are. So all the models that you see nowadays, GPT, they are all autoregressive. What I mean by autoregressive is each word, like the next word that you want to predict, is based on the previous words. So that is what autoregressive means. So all the models, not only text models, even the multimodal LLMs that are coming nowadays, text to image models, they are all sequential models. That means every next token or next image is based on previous token. So we saw the problems with some of the traditional language models, and then we came like studied what sequential modeling is. So like in sequential modeling, we studied RNNs and CNNs, and what are the problems with RNNs. So one of the problems with RNNs was that it's not able to handle long term dependencies. What I mean by that is, if the sentence length is let's say 10 or 20, it will be able to capture the meaning of, or relate the first word with the 20th word. But if the sentence is a big paragraph of, let's say, 1,000 words, it won't be able to capture the relationships. For example, if there is a sentence in the first line of the paragraph, uh, let's say John says a particular thing, and in the last line of the paragraph, a question is asked, what did he say? So he here can refer to John. So the model has to make, as humans, we can make this relation ki, oh, this he corresponds to John, like the term he maps to John, but we need to teach models to do the same. So RNNs cannot do that, and that's why we studied LSTMs and GRUs, which can handle these things better, long-term dependencies. And then we studied encoder decoder, which is a model we can make using LSTMs. So encoder decoder is not like, to study attention, you need to know what encoder decoder is. So if you see the first part here, it represents the encoder and decoder. So what encoder does is, whatever input data set is, for example, let's say you are doing the task of language translation, like you are converting English to German or French in language. So first you'll give the English sentence. Let's say my name is Rajat, or this is NLP Workshop. So what X1, X2, X3, Xn represents is the sequence of words. So X1 will represent the first word or the first token, which is my. X2 will represent name, X3 will represent is, and X4 or Xn will represent Rajat. And then you will encode this information, all this information. And this, as you see, the last layer, all the information of all the words, all the sequence will be encoded, will be passed to all the subsequent layers. And in the last layer, all the information is compressed or encoded for the whole sequence. Now the last layer is called the bottleneck layer. The reason being, let's say this is right now four, like the sequence length is four here. But let's say the sequence length is 1,000 or 2,000. Then all the information has to be encoded in one sequence. But it can be a bottleneck when it can happen that the very first token can be relevant for the particular task, but the information is lost over time as it is encoded and passed through all these layers. The information is lost. So this encoder layer, the encoded information will not contain the first token or the information passed through the first token. So that's why it's known as bottleneck. Now the task, and that is what attention mechanism solves the problem of bottleneck layer. We'll see it how. First, let me tell you what decoder is. So after all this information is passed, is compressed into this like encoding layer, it is passed to the decoder. And what decoder does is it takes the information. Each decoder model will take the information and convert it to the corresponding French or whatever the language is. So 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 in general, decoder decodes the information which it gets from the encoder. So this was like the task of machine translation, and like the problem here, as I said, is this bottleneck layer. What if the all the information is not properly encoded here? So how attention solves it is, for example, let's say this particular word was very informative or very important for decoding certain word. For example, let's say name in a certain language can be, let's say, X. In French, name like is converted to, let's say, a particular word X. And so at this point where it is actually decoding name, translating to name, so it will focus more, give more weightage to that particular encoder sequence X2 instead of giving more importance to X3, Xn, X1. And if you think intuitively, it makes sense, right? Even like if we translate a particular sentence from uh, to any other language, if we have to translate from a given sentence to another sentence, we'll focus for the corresponding output sequence. We'll only focus on that part which we are converting at that point. So so the same idea is with attention. So there are basically two types of attention. One is cross attention and second is self attention. So all the transformer models that you see right now, self attention or some variation of self attention is used there. But since we are starting transformers in the next lecture, we'll cover self attention in the next lecture. Here in this workshop, we'll cover cross attention. So as I said, it overcomes the limitations of traditional sequence to sequence models. And so, as I said, so this is just a heat map of, for a translation from English to, I don't know what language is this, but some language. And the light spots that you see are the sequences which are relevant, which are the corresponding sequences in the other language. For example, when let's say the word 1992 is represented like this 1992 in English also and in any other language also. The word agreement in English is represented as accord or some this word in other language. This word European is represented as this word. So it is only while converting or like translating the language, it is only focusing or giving more weightage to that particular word which it is translating, and it makes sense intuitively also if we think about it. So, so there are basically different variations of cross attention too. So here, for like the first ever attention paper that came was in 2015, and like Bharda now is the author name who published the work. So it's also known as additive attention mechanism. We'll see why it is called that. So here again, so in the paper that was published, the author used the encoder decoder model that I showed for machine translation task to like implement the attention mechanism. So there are three to four, like four major components in the attention mechanism, attention mechanism. First is encoder that we saw, which encodes all the information of the input sequence. Then there is decoder, which decodes the information that it gets from the encoder. And then there is alignment score, which aligns the relevant encoder information at time t and the decoder time step t. So, for example, as I showed in the encoder decoder sequence, let's say for decoding y2, it needs x3 encoder state x3. So the alignment score will be high for x3 and y2 for the decoder state. So that is what alignment score does. So for any step of decoder, it gives more weightage to particular to the corresponding states in from the encoder. So we'll see it in more detail. And then from the alignment score, we get the attention weights, how much attention to give to each sequence in the encoder. Then so so as I said, right, the alignment scores, how they are computed, as we have encoder, we have decoder, and then we take one layer neural network which has one input layer, one hidden layer, and one output layer, and then we compute we do this computation. As you can see, ETI is equals to V transpose 10H and into this W1 ST minus 1 plus W2 HI. So what it is W1, W2 are the parameters of the neural network, and 10H is the activation function which is being used, and ST minus 1 is the uh, corresponding encoder state information which is relevant for that particular decoder state, and HI is the hidden state. So you compute this for all the you compute this alignment score for all the encoder states x1 till xn, and then you take a softmax. So after taking softmax, you get a attention score. So for example, x1 you get the attention score of, let's say, 0.1. For x2 you get a attention score of 0.7, and for x3 you get a attention score of 0.2, and you at a decoder step 2. That means at decoder step 2, while translating the language, you have to pay more attention to x2 because the attention score is 0.7. So initially, in the simple encoder state, encoder decoder, what was happening was, as you saw, all the information x1 till xn was just merged and given to the decoder as it is. Now, after attention, the attention, it will be weighted by its attention. For example, as I said, 0.7 into x2 plus 0.2 into x3. What it does is, the model will know, okay, since x2 is multiplied by higher attention, it has to focus more on x2 for that particular hidden state. So that is the idea of like cross attention. And this particular attention, as I said, as you can see in the end, the last equation, you take the summation of all the attention and the encoder hidden states. That's why it's also known as additive attention. And then a second variant of cross attention came, and it's known as Luong attention mechanism. Luong was the author who published it. So here, in the alignment state, what we do is we just compute we take the dot product of that TF decoder state with the encoder state information. And that's why it is also known as multiplicative attention. And that is how you calculate the alignment score, and then you apply softmax and get the attention score. So previously, in the previous cross attention, we were doing all this using a neural network and getting the alignment score. Here, they just take if you are at decoder state 3, you just take the dot product with encoder state 3, and you get the alignment score. And then you apply the softmax activation function, and you get the attention score. And again, you will like do this for all the states, all the decoder states, multiply it by all the encoder states and get the attention for that decoder state. And then you will use that attention to, put more weightage to whatever encoder state the attention score is high. So this was cross attention. Now we'll go over the coding of RNN LSTM, the attention mechanism. There you can see how it is actually implemented.
Um, okay, so like first we will go through the data preparation, and like we already went through it in the previous workshop, so I'm gonna skip it. And then there is just the like data exploring, and we have directly downloaded the data from the Stanford website. And then we are converting the data into a data frame, and then we are just text processing, and then we are doing the embedding part that Prabhakaran explained in the previous code. And now I will start explaining, like, oh, this is how the embeddings look like. These are the embeddings for the process text. So now I will start with the RNN part. So we are gonna do simple RNN implementation, and like what we are gonna do is it has like three main parts. First, like initialization. There are gonna be three layers. First is input, second is hidden, and third is output layer. And we are going to do forward pass to these layers. Like we are gonna go from input to hidden, then to output, and then we are gonna do backward pass to find gradients and find error, and then kind of fix it. So we are like capturing the right output. So, s- um, this is like the sigmoid function. We are just defining sigmoid function. It just gives a result between 0 and 1. Then there is we are going to use it for doing the forward pass. Then there is sigmoid derivative. There is tan derivative function, and we are going to use it for doing the backward pass because we are going to find derivatives and the gradients. So that's why we are going to use it for. Then we are just initializing weights here in the like simple RNN class. And these weights are basically for connecting the input layer to hidden layer to output layer. That's why weights are used, and that's why the weights are changed when we are doing the backward pass, which is also called backpropagation. And like in RNN, we do backpropagation with time, since we are doing it for each time step. And this is a function to just reset steps after each time steps. And now this is a function for the forward propagation that we are going to use later. So in the forward propagation, we are just going to go through the input to hidden states. Then we are going to go to the next hidden state until we are done with it. And then we'll go to the outputs like layer. And it's going to be a sigmoid layer where it will give output to be 0 or 1, because that's what output the sigmoid layer gives. It's a function for that. And then this is the propagation function. In this, we are gonna go from the output layer to the hidden layer, then from the hidden layers to the input layer, and we are gonna find errors. So here we are like finding errors and fixing it, like changing the weights according to errors. So the error is basically um it's the like it's the difference between the target, like what you want it to be the prediction and what your actual prediction is. So that's how the error is calculated. Then we are also clipping the output. This like for the backpropagation, this is to avoid the problem with vanishing gradient that that was explained in the last class. And yeah, then we are just gonna initialize the simple RNN model. And here the input size is given to be 100, which is just like it can have like 100 inputs at a time. And the hidden size is 50. So it's not that for a hidden state, it will take account to 50 previous hidden layers. It's more like it can hold, it's like a memory that it can hold 50 embeddings at once. So this is, we are just preparing data for sentiment analysis, and like we are just splitting the data into train data, validation. Then yeah, training the RN model. So here we are gonna train the RN model. As I said, we are gonna first do the backward forward pass. We are calling the forward pass function. Then we are going to compute the error, which is like target minus predicted. We are using the binary cross entropy loss, and then we are computing, like we are calling the backward function to update the weights that we initialized earlier. So that's what's done, and this is the output. So here it's like calculating loss. As you can see that the loss is going from 0.69 to 0.56. It should go more below if we like continue with the epochs. Epoch is basically how much time you're running the same um like same function again and again. So it goes through all data once in the first epoch, then it goes again in the second epoch. So that's how it works. And usually there can be a lot of epochs according to how your model is performing. I've just done 5 here to show how it looks like. Then we are just evaluating the model with the like validation data we split, and this came out to be the accuracy, which is 0.7, which is not that good and not that bad. So it's good for the simple RNN we are using. And then this is the visualization code. It basically tells us like how the, like this is the output for the code. It tells us how the RNN is looking at the data. So for example, for the first review, it would take the words like critic, need, review, class, quality, and then predict it as like the first word as predicted to be one. One is basically it is positive word, positive sentiment word, and zero is negative, and that's how it's like predicting between 0 and 1. And then it keeps predicting through the words. Like these are the 4 reviews that I have like shown the output of, and it just keeps predicting word until the last word, and it just takes like probability of all words into account to predict the sentiment of the output sentiment. Then so this was the RNN, and now we are going to talk about the LSTM, which is long short term memory layer. So it's a type of RNN which helps to fix the problems that we have with RNNs, as Rajat told. So here we are using bidirectional LSTM. There is also like unidirectional LSTM, just a normal LSTM. So we are using bidirectional because we are gonna go with the forward pass and the backward pass at once to like capture more data. So the code for the LSTM, the layers used are like it is pretty same as the RNN code. Just the like only difference is that we are using the like a new layer which is LSTM layer. We are importing it from the TensorFlow Keras library, and that's where we are using it from. And yeah, like this is the output of that LSTM. So as you can see, I have just did 5 epochs for this as well, and it is pretty good. From the accuracy of 0.6, it went to 0.9 pretty quickly. But sometimes it is not that good to have this quick increase in accuracy because the validation loss is also increasing. It should decrease. So it shows that maybe it is overfitting or something. So you can always go and fine tune it, but this is how you write the like code for this. Then there is a GRU model, which is gated recurrent unit model, and it is a good version of LSTM. Like it is more easy to compute, it gives better result. So yeah, I've used this model, and the like code is pretty same, just the GRU layer comes instead of the LSTM layer, and it is imported as same way like the LSTM layer. So it's pretty same, and the output is also same because we are just doing 5 epochs. So it's not telling much about like the difference between those two, but like you can always go and implement more epochs. Just like for the Google Colab, it has limited memory, so it doesn't allow a lot of computation, but yeah, you can always do on your laptop. And then this is the comparison like code between these two models. So here it's the accuracy and here is the loss. For the accuracy, it's pretty good. Like the accuracy is increasing, but for the validation accuracy, which is not that good for both the models, it's not increasing. So apparently, what we want is both the actual accuracy and the validation accuracy in should both increase, because that's when we know that the model is not overfitting. And then when we look at the loss, like we can see that the loss is going down for both the models, and it is pretty similar. But the validation loss that we are checking the loss and the accuracy on the unseen data, that's validation loss. It's like going up, means that the loss is increasing. So it can show that it is overfitting, or it is learning the data which we are training it on. It is not learning the patterns of the like data. It is just learning the whole data. So now we will look at the code for Badao attention. um For this, it's also pretty much same. It's like using the code from the RNN implementation that we did. We are just going to look at this attention layer for this model, and like it's pretty much same as Rajat explained with the like pseudocode or yeah. And what we really do here is we calculate the sum of the attention scores that we are calculating, and then we put this layer in the RNN. So here it is, I think. Yeah, we are just putting the attention layer here. As like in the RNN there was input, hidden, and output layer. We are just putting attention layer in the middle, and attention layer basically calculates the attention scores, and it is basically like it finds the relevant things and just keeps that instead of keeping everything to predict, which is like important that data. So this is the output of the layer. So these are the layers, like it's input, and then it's the embedding, then it's the simple RNN, and then there is the attention layer we are using. And then there is a dense layer, which is like a full layer, which we are using to find output. It has the sigmoid function in it. So I'm also like using 5 epoch for this as well. And as you can see, the accuracy is pretty good. It's the same data if we compare to the LSTM up here, LSTM or GRU. The accuracy is good, but here it's better. So having like attention, it like makes it better. So for the long attention, the code is same as the other attention layer, but here we are just doing the dot product instead of summing the attention scores. So and the output is also pretty much same. The output changes as you increase the epoch, as you change the hyperparameters. So I've used pretty much same for both of them, so that's why the output is pretty much same. Yeah. And that's the code for like RNN and the attention mechanisms. Yeah.
So yeah, for this week, we didn't cover any new concept because we knew that this is midterm and everyone will be busy with their midterms. So the transformer architecture, as I said, will be covering in the next workshop. So this code is shared in the Discord channel, and you can go over the code and run the code yourself, and make some changes, play with the RNN and LSTM and attention architectures. You can change few things, add one layer, delete one layer, and see how it impacts the performance. This is for a simple sentiment analysis task. You can like use the same RNN LSTM code for also doing the machine translation task, and see you'll easily get the data set online through Kaggle or something, and you can try it yourself and play with it. And if you have any doubts, you can contact any of us and on the Discord ask your doubts. So yeah, see you next week, same time and same place.